Hello, this is Lab 3 Circuits for Physics 2212. The introduction, this is the main purpose and fundamentals. The purpose was to predict the behavior of circuits with resistors in series using multimeter and examining the behavior of resistors and capacitors. Our fundamentals included Kirchhoff's loop law, Ohm's law, the potential difference across capacitor, and the RC time constant equation. The main findings are verifying Kirchhoff's loop law and finding that increasing resistance in an RC circuit increases the charging and discharging time of the capacitor. We use Kirchhoff's loop rule, Ohm's law, and potential difference across capacitor. Loop law shows you that sum of voltage in a loop is zero, and Ohm's law tells you that the change in potential across resistor is I times R, and the potential difference across capacitor shows that the potential difference across capacitor is related to the charge on the capacitor and the capacitance of the capacitor. Our main assumptions are that the wires in the system are ideal and the batteries are ideal. These assumptions simplify the calculations and make it easier to analyze, and under the conditions that we're working in, the fact that these assumptions don't hold in real life does not really affect the overall system that much. Here's our main diagram of the two resistor circuit. The system is the circuit and the surroundings is everything else, and then later we switch to the RC circuit and that will be the system. These are the initial conditions for both of the circuits, and then the experiment details. So initially we're setting up the circuit with the two batteries and the resistors, and then we're using ammeters and voltmeters and switching them around to measure different things. Then later we're setting up RC circuit, we charge the capacitor, and then we discharge the capacitor, and we time both, and then we use the same setup with two light bulbs to demonstrate an RC circuit with higher resistance. So here's some circuit analysis for the two resistor circuit. Using Kirchhoff's loop rule, we found that the current was 0.0204 amps, and then for the actual circuit we used a slightly higher resistor, and we also had less potential difference in the battery, so our measured result was 0.0189 amps, which is only slightly lower than the calculated value, which makes sense because our actual potential difference in the batteries was less than the assumed one, and the resistance is slightly higher. Results continued. We did some things with the ammeters and the voltmeters, but the main thing here is that we confirmed Kirchhoff's loop rule, where we remeasured the two batteries, remeasured the resistors, and then when we add it all up, we get zero, and that confirms the loop rule. So then this is some more stuff where we're changing how we're using the ammeters and voltmeters, and then this is the voltage graph. So we have the batteries on the left, and then we have the resistors changing the voltage on the right. Then RC circuit, we did not have specific light bulbs to us, and the two given to us were the same. So for just one bulb, it took 32 seconds to charge and 37 seconds to discharge. For two bulbs, it took 74 seconds to charge and 54 seconds to discharge. And then these are the loop rules for each one, but those don't really matter that much. So we use the equation for time constant of RC circuits, which is in the lab instructions, which is derived from solving the differential equation. Rearrange it to isolate T, and since we don't know the resistance of the bulbs, we cannot calculate the time constant exactly, but we can see that the time for two light bulbs, which has double the resistance, will be twice as long as the time for one. Some sources of error is measurement of the stopwatch, the multimeters could be wrong, and the numbers on the resistors and capacitor could be slightly inaccurate. Some similarities and differences between the measured values and our calculated values. The values of the battery were slightly lower than we assumed, and the batteries lost some charge, which would not happen with ideal batteries. And some similarities is that we were able to get the sum of the potential differences of zero, which confirms Kirchhoff's loop rule. And then also when measured, the capacitor did not take exactly twice as long to charge and discharge when we added a second light bulb, and this is likely due to error, probably with the stopwatch. Discussion. What if? So if the capacitor was charged with no resistor, in the ideal model it would charge immediately and the RC constant would be zero, and the limiting case is that the capacitor would charge infinitely quickly. In actuality, it would still take some time to charge the capacitor because it's impossible to have a circuit with zero resistance, and the wires would have some resistance, causing the capacitor to charge quickly but not infinitely so. So we measured the charging with no resistor to be about 5 seconds, which is different from the predicted time of zero because the wires in the ammeter have some resistance in real life, but in the ideal situation they just have no resistance. So in conclusion, we found that Kirchhoff's loop rule holds in real life, and that using Ohm's law we can find the current in the circuit, which in this case was 18.9 reality and 20.4 milliamps calculated, and the difference was due to slightly different battery potential differences and very slightly different resistances. We also found that in an RC circuit, the greater the resistances, the longer the time it takes to charge and discharge, and an ideal situation would be twice as long as charge and discharge.